The reason impurities aren't a bad thing is because they impart different properties on substances. And best example would be iron plus carbon. Not a lot of carbon, but a little bit. And you end up, there's no chemical reaction here, but you end up with steel. This is just an alloy. Um, so we've embedded carbon into the iron and it changes its properties. The steel is more rigid, less bendy. It's stronger for its weight. So the same size structure made out of steel is much smaller than the and much less weight than the same size structure made out of iron. And it's much more corrosion resistant than straight iron is. Other examples are like from the alchemy lab, when you mix copper and zinc, you get brass. So the brass has better properties than the zinc and better properties than the copper. I mean, depending on the situation. Or you could go copper plus tin and you get bronze. Impurities in sort of a crystalline structure like a diamond could impart color, or emerald could impart color. So the impurities are definitely not necessarily a bad thing. All right, so write the vapor pressure of ethane and the vapor pressure of ethanol here. So I found a couple charts. And so with vapor pressure, the two things that matter for vapor pressure are most importantly the substance itself, and then also the temperature. So I'll just pick a temperature. I'll pick like room temp. So make it easier on myself. I'll say room temp is 20 degrees, even though it's a little warmer than 20 degrees. So 20, and then I'll take this line over here, poorly drawn. This is in millimeters of mercury, so 100, I don't know, so like 76. I go make it really easy. 75 millimeters of mercury. All right, so 75 millimeters mercury. This was for sorry, this is for ethanol. All right, and then I got another chart down here. So this is ethane vapor pressures, and well, geez, I'm gonna have to look at it again. I don't have a temperature that high. So 272, that's about 0. And this is in pascals. So this is, what do we got here? 2321000 pascals. So we're gonna have to do a little unit manipulation here. I need to get to 0. So it looks like, I don't know, let's go with 2 millimeters of mercury, and that's at 0 degrees Celsius. And this is at 0 degrees Celsius. All right, so I'll do a quick transfer here. So it's 2321123. And that's pascals. And then for every 1,000 pascals, that's 1 kilopascal. And then for every 101.10, no, 325 kilopascals, that's 760 millimeters of mercury. So we're just doing this so we can get the units to be the same. All right, and so those numbers, those conversion factors just came off that Chemistry 121 set of notes from the gas laws. All right, so I've got 2, 3, 2, 1, 1, 2, 3. I guess I didn't need to do that. And then times 760 divided by 101.325. I get 17409 millimeters of mercury. Okay, so one's got a vapor pressure of 17,000 at 0, and one's got a vapor pressure of 2 at 0. So those are obviously dramatically different. And so the question is why do they have dramatically different vapor pressures? Well, ethane is this molecule. And so I've got 2.2 electronegativity and 2.5 electronegativity and perfect symmetry. So this is a non-polar molecule undergoing dispersion. forces. That's it. Just dispersion forces, which are the weakest. And then up here, I've got oops, didn't mean to do that. So here I've got H bonding. So another one of these ethanol molecules could be hanging out like that, and I have an intermolecular force here and an intermolecular force here, where this is a partial negative, partial positive, partial positive, partial negative. So there's good attractive force there from a strong dipole. So that's why the vapor pressure for the ethanol is going to be so much less than the vapor pressure of the ethane. Okay. What do we got next? Draw the structure for isopropyl alcohol and talk about how it can be miscible in water. All right. So the structure for isopropyl alcohol, it's I go H3C, C, H3, and then there's a OH and an H. This is a tetrahedral shape around that carbon. And I got a partial negative here and a partial positive here. So I have a nice little synergy with a water molecule where that oxygen and that hydrogen bound up, that oxygen and that hydrogen bound up. So isopropyl alcohol and water will mix together very easily. The other important factor with this is nonpolar and this is nonpolar, but overall this molecule is small. If I were to keep adding CH2 groups to this, there'll be a point where this non-polarness outweighs the polarness and makes this so it is not soluble in water. But that's not the case with the isopropyl alcohol. It is miscible. All right. Explain how these calculations used to determine the radius. All right. So first off, this equation. So I've got two Pythagorean theorems here. I have this triangle and I have this triangle, and they share this wall here. And one of them, it's the hypotenuse, and the other one, it's just an adjacent that word's escaping me. An adjacent line. Let's go with that. All right, so I got my hypotenuse and two A's, because that's the A here and an A here. So double A squared. And I take this and I substitute it into the B squared. And that gives me A squared plus A squared plus A squared, which is 3A squared. Then I square root both sides. I end up with square root of 3 times A. And then let's see, I rearrange this. Sorry, I need to erase some stuff. I solve myself for A, and then I've got radius, 4 times the radius divided by the square root of 3. And so that's going to assist me to determine that. So if I know this distance and this distance, I can figure out my R. And my R is the size of my atom, the radius of my atom. So knowing my lattice point distances will get me to my R. So all I'd be doing with this one in this case would be to rearrange this. So I go, let's see, what would that be? A times the square root of 3 divided by 4 equals radius. Okay, so I do X-ray crystallography on this substance. I get an A value of the lattice point distances, plug it into this equation if I know that it's body centered, and then I get the size of my atom. Cold is formed, so it's face centered. All right, so we're looking for the face centered calculation and the equation for that. So if you look at that one up, it's why does it keep changing on me? A is equal to the square root of 8 times r. And if we look up the radius of a gold atom, let's see. So I gotta grab a table here. Looks like, wow, that is a tiny, tiny font, isn't it? Gotta go to glasses, and it looks like it's 144. All right, so equals 8 squared times 144 picometers. And so then, let's see what we got there. Square root 8 closed times 144 is 407. So 407 picometers would be the distance on that face-centered cubic from here to here would be 407 picometers. Right, a short explanation of X-rays, X-ray diffraction. So first thing you got to do is crystallize the substance. If it's not in a crystalline form, this doesn't work. So I need a crystal lattice structure to even accommodate this. So if I'm talking about a substance that's normally a liquid or a gas, I need to make sure that that liquid or gas can be frozen and crystallized. Because if it can't be, then you can't do this, can't do X-ray crystallography, because I mean, that's how the diffraction pattern works. So what you end up with are layers of atoms. You use X-rays because X-rays, the range of X-rays is the range of the distances of these lattice points. So you can't use gamma rays or UVs or visible light because they're not the right length. And what we're trying to do is get some constructive interference to make lattice patterns show up on as pinpoints on a screen, basically. So if I shoot X-rays and it hits this one here, they're going to have an indice of refraction. They're going to, or diffraction, they're going to turn. Okay, so when they turn, I don't know, I wrote a squiggle over the top of that. When they turn, they're still going to have their wave pattern. Okay, so if I tune this correctly, these waves are going to be in sync with each other, but this one had to go a further distance. The distance, when it's in tune, the distance is plus one wave. So one wave distance. So these guys are in sync with each other, but this wave right here turns out to be this wave right here. So this one becomes, erase that. I use a different color. So when this wave goes in, these two guys are in sync, but this one travels a longer distance. So because it travels a longer distance, it hasn't left the substance when it is reflected because it went that longer distance. But the wave in front of it, which would be this one, is now in sync with this other wave. Okay, so that same situation can happen 3 layers down. Hits, and then you'll get these guys in sync again. If it's tuned correctly. And so these form a constructive interference. That constructive interference builds up the X-ray into an amount of X-ray that can be seen or detected on the correct type of screen. So what you would do is you would take your crystal and you would rotate the crystal through this X-ray field, tuning the field until you get X-ray scatter patterns. And then we can measure the distance. So when this happens, you end up having like a screen that's got dots on it all over the place. And you can measure distances between the dots and determine what type of structure it is, and then the distances between the lattice structure, those points, and then you can calculate the radius of the atom. And a short paragraph on Rosalind Franklin. All I'll say with this is, let's see. Oops. Abused is definitely the correct word, even though there was no physical abuse. It was all mental. She was told that she literally was told that she was ugly. She was told that her work wasn't important, and she was told that she wasn't very good at her work. All of which were lies. I'm not going to comment on her attractiveness level, but the important parts were that she was told that her work was worthless, which it absolutely wasn't. Her work was so good that the people who got credit for it, which are Watson and Crick, used her calculations to verify the things that they thought up in their heads. That she was the science and the math behind the thinking of other people. So unfortunately, she passed away before any of this could come to light, and she could get properly recognized. She's the person that took the photograph. Photograph number 51 is the famous one. And that photograph led her into some calculations that proved that the double helical structure was the correct structure for DNA. And that image was stolen by Maurice Wilkes, who gave it to Watson and Crick. And when they saw that, along with other information that they had gotten in other ways, they realized that they could build different types of structures that could fit that model with that image. And then having the image, it verified which of the structures actually worked. So that's why they get credit for it. And that's it for this homework assignment. Stop this recording.